Hi, this is Sung. I'm the director of Sky Academy, and in this episode I want to build on some of the theorems and axioms that we've been working through, and in the last episode in particular we worked through the equal intercepts theorem, yes? And we're going to use that, or build on that, to show or prove another theorem to do with equal intercepts, and that is intercepts on the midpoints of sides of a triangle, okay, or on a triangle. So this basic theorem says this, right? So if you've got a triangle, let's say this triangle here, which is ABC, right? And you've got midpoints D and E on sides AB and AC, so these midpoints here. This theorem basically says that the line joining the midpoints, that line there, is going to be both parallel to the third side and exactly half the length of it, okay? So in words, the theorem says this: the straight line joining the midpoints of two sides of a triangle is both parallel to and half the length of the third side. And we're going to set out to prove this. So I've sketched a base triangle or a basic triangle to help us to prove this, right? And so this is what we've done, all right? We've got triangle ABC with midpoints D and E of AB and AC respectively, which are these 2 points being the midpoints of AB and AC respectively, all right? And we've also constructed EF such that EF is parallel to AB. So let me just explain. We've also constructed, and I've drawn this construction line in red. We've drawn this construction line, or produced is the right word. We've produced this construction line such that it is parallel to AB. All right, cool. Now, the aim of this, there's two aims, remember? There's twofold aims. The first aim is to basically show that DE is parallel to BC, okay? We're gonna try and prove that that line there is parallel to that line there. And the other one is to prove that two lots of DE equals BC. So in other words, we're trying to show that this side here, right, is half the length of this. Now, one of the ways that we're gonna do this, right, is if we can show that this is a parallelogram, and this side is equal to this side, and if we can also show that these two triangles are congruent, which basically is that this side here is equal to that side, then these two sides combined are going to be twice that side there, yes? Good. So that is basically the way that we're going to navigate our way through this proof. We're going to start off by doing this. Step one of this proof is basically take this triangle here, which is ECF, and this triangle here, which is ABC, and we're going to show that we're going to try and show that they're similar. Okay, so that's going to be step one of our proof. So let's work that out. All right. So step one, in triangle ABC and triangle EFC. All right. Angle C equals to angle C. They're common to both. And we also know that, for example, this angle is equal to this angle because they're corresponding angles on parallel lines, okay? So angle ABC is equal to angle EFC. Got it? So basically what we've done is we've shown that this angle is equal to this angle. Let's put a 1 there. So the angle 1 is equal to angle 1. Angle 2 is equal to angle 2. And angle 3 is automatically equal to angle 3. But we don't need to write that in the proof because just showing that two pairs of angles is equal is enough to show that these two triangles are similar, okay? So therefore, triangle ABC is similar to triangle EFC, and the reason is that they're equiangular. Good, got it? Which basically says this, right? that EF to AB is going to be in the same ratio as EC is to AC, right? Which is 2 to 1, right? So in other words, if this is twice the length of this, right, then we know that this is half the length of that, and this will be half the length of that. So in other words, these two sides will be equal, these two sides will be equal. Does that make sense? All right, so we're going to do that. So we've got, for example, AC to EC is going to be equal to AB. So that's basically what we've written down. We've written down that AC to EC is equal to AB to EF, which is 2 to 1. Does that make sense? Good. And the reason why is they're similar triangles, which basically means that EF is going to be equal to AD and DB, right? So let's write that down. EF is going to be equal to AD, and it's also going to be equal to DB. All right, so all those sides are going to be equal, okay? Now what we're going to do is we're going to do step 2 of the proof, which is to show that these two triangles here are going to be congruent. And we can do that basically using SAS, right? Or AAS as well, okay? But SAS is probably the one that we're going to use, and we're going to show that these two pairs of sides are equal, and the included angle is also equal, therefore they're congruent, okay? So step 2 is this. In triangles ADE and triangle EFC, AD is equal to EF, and the reason why is that we previously showed that. What else? We know that AE is equal to EC. Why are these two equal? Well, it's given in the question, right? And finally, we've got angle BAC is equal to angle FEC. And why is that? Corresponding angles. All right, which means that triangle ADE is congruent to triangle EFC. The reason why they're congruent is because SAS, side angle side. Got it? Cool. So from there, we're going to set up a couple of things, right? From there, we're going to say a couple of things flow out of this, right? So let's work out what flows out of it. Step 3, DE is going to be equal to FC. Do you see that? That is going to be equal to that. Do you see that? And the reason why is congruent triangles. What else? Okay. What else flows out of this is that DE will be parallel to BF, and the reason why is because these two triangles are now congruent, which means these two angles are congruent, okay? Oh, these two angles are equal, okay? So, angle AED is equal to angle ECF. And again, the reason is congruent triangles, which means, and this is aim 1 proved, therefore DC is parallel to BC, okay? And the reason why is because equal corresponding angles lie on parallel lines. Got it? So that's premise 1 proved. And then we've got to show premise 2. Now, this comes this way, right? If we can show that these two lines are parallel, and we just did, which means that is parallel to that, what that then shows you is that DE must be equal to BF. Does that make sense? All right, so we're going to show that. All right, since DE is parallel to BF and DB is parallel to FE, therefore quadrilateral DEFB is a parallelogram. Therefore, DE is equal to BF. Got that? So we know that these are equal. These two are equal. Right, now, we also know that BC is equal to BF plus FC. All right, so BC is equal to BF plus FC. So we know that BC is equal to BF plus FC, and we know that BF is equal to DE, and we know that FC is also equal to the length of DE. So BC is equal to 2 lots of DE, which is basically premise 2 proven. See? Good. Okay. So that is a proof of this particular theorem here. It says the midpoints of 2 sides of a triangle, when joined together, right, create another line that's parallel to the third line or to the third side, and is also half the length of the third side. Right? And all you have to do, instead of proving this out, if you see that in a proof that you're trying to prove and you want to use this piece of knowledge, instead of proving it, you can just use that piece of knowledge, and you can say, as your axiom or your reason, the midpoints of the side, midpoints of sides on a triangle. Okay, and that's all you need to say. Right? Good. Well, thank you very much for watching, and we've pretty much wrapped up or summed up the plane geometry section of the 2-unit course. Thanks again. Bye.